Okay, hello everyone. Let us continue the second part of today's class. Excuse me. Okay, where G is defined as PR over PT denotes the power gain of the channel or the reciprocal of the path loss. Okay, so now you can know the path loss is equal to PT over PR. Okay. So next, okay, let us go to section 4.6.2, Rayschen fading. Okay. Rayschen fading occurs when the received signal consists of two components. A random portion that fluctuates. Okay, what is the meaning of the word fluctuates? Okay, let us see the handout. Okay, handouts, chapter 4. Okay, today. Okay. Okay, so let us search fluctuates. Okay. Okay, let us see page 217, problem 1. What is fluctuates? Okay, solution: to change especially continuously and between one level or thing and another. Okay, this is the meaning of the word fluctuates. Excuse me. Okay, so let us go back to the slides. Okay, that fluctuates in time and a non-fluctuating part. Okay, where we know that fluctuates is a verb, and fluctuating is the adjective of fluctuates. Okay. One way in which this might occur is if some of the transmitted signal energy propagates directly to the receiver and some of it gets scattered off objects along the path between the transmitter and the receiver. Okay, under Rayschen fading conditions, it can be shown that the PDF of the absolute value of h of k has the following form. Okay, let us see this equation. F of the absolute value of h of k of x is equal to 2x times k plus 1 over g. Okay, times exponential negative k minus k plus 1 times x squared over g times I0 of 2x times the square root of k times k plus 1 over g. Okay, for x is greater than 0. Okay, so and how about when x is smaller than or equal to 0? Okay, although this equation does not tell us, however, you should know that when x is smaller than or equal to 0, f of the absolute value of h of k of x is equal to 0. Okay. Where I0 is the zeroth order modified Bessel function of the first kind, and k is called the Rayschen k factor, which is defined as k is defined as power in direct component divided by power in scattered component. Okay. It follows from this definition that the Rayschen distribution should become identical to the Rayleigh distribution when k approaches 0. Okay, since, okay, or because in that limit all the received energy would be associated with scattering. Okay, because when k approaches to 0, the power in direct component approaches to 0. Okay, so all the power is in the scattered component. Okay, so all the received energy would be associated with scattering, which is the assumption underlying Rayleigh fading. Okay, what is the meaning of the word underlying? Okay, let us see the handout. Okay, page 220, problem 1. What is underlying? Okay, solution used to describe something on which something else is based. Okay, so let us go back to the slides. Okay, which is the assumption underlying Rayleigh fading? Okay, because I0 of 0 is equal to 1. Okay, you may ask a question. Why does I0 of 0 equal 1? Okay, if you ask this question, it is very good. Okay, let us use the MATLAB to find the value of I0 of 0. Okay, this is the MATLAB. Okay, and you can press F1 on your keyboard and open the help browser. So now we want to search about the Bessel function. So in the search documentation box, we can input Bessel. Okay, so we can see that there are many different kinds of Bessel. Okay, so let's see what is the Bessel function. What kind of Bessel function we are considered. Okay, I0 is the zeroth order modified Bessel function of the first kind. Okay, so back to the MATLAB. So modified Bessel function of the first kind. Okay, so this one, Bessel I. Okay, so let us see the description of this function. I is equal to Bessel I of nu z computes the modified Bessel function of the first kind, I nu of z for each element in array z. Okay, so we can know that we only need to copy this command. Okay, and paste in the command window, and we change the nu, which is the order, into 0, and change z also to 0, and end, press the enter. Okay, so then we have, okay, Bessel I of 0 is equal to 1. Okay, which is the same as our slides. Okay, because I0 of 0 is equal to 1, okay, it is clear that in this limit, equation 4.63, okay, let us see equation 4.63, okay, is this equation. Okay, so thus, in fact, become equivalent to the Rayleigh distribution as defined in equation 4.62. Okay, let us see equation 4.62. Okay, this equation, we have seen this several minutes ago. Okay, so how to show that? Okay, equation 4.63 become equation 4.62. Excuse me. Okay, so let us see the handout. See the blackboard. Okay, so let us go to the blackboard, and because I do not have a blackboard, so I use the Microsoft Word instead. So this is chapter 4. and page 222, problem 1. Okay, let us see this. Okay, and let us alter this. Okay, prove that when k is equal to infinity, comma, equation 4.63 does in fact become equivalent to the Rayleigh distribution as defined in equation 4.62. Okay, let us see the solution. Okay, so from equation 4.63, we know that. Okay, let us see equation 4.63. Okay, so this equation. Okay, let me combine them into one line. Okay, good. Okay, so this is equation 1. Okay, good. Okay, when k approaches, this should be 0, not infinity. Okay, when k approaches to 0, equation 1 becomes so k approaches to 0. So we can delete this term, and plus 1 can be deleted. And k is equal to 0, so this term disappear. And k is equal to 0, this term disappear. And we can delete term plus 1. So k is equal to 0. This is equal to 0, and this term disappear. So this square root is also equal to 0. So 2x times 0 is equal to 0. And we know that I0 of 0 is equal to 1. So we can also delete this term. So let us call this equation 2. Like this. So let us see 2x over g times exponential of negative x squared over g. Let us compare with equation 4.62. We can see that it's just the same as as equation 4.62. So let me change it to comma. Which is the same as the Rayleigh distribution as defined in equation 4.62. So insert a black square. Means QED. This should be small w. So it is very simple. Back to the slides. Okay, so we have proved this fact. Okay, and the following is problem 4.2 and problem 4.7 and the references. Okay, so we have finished teaching chapter 4. Okay, and let us see. Okay, since the final exam is approaching, I will not give homework 4 to relieve your pressure. Okay, and here is the Chinese translation of this English sentence. Okay, so next, we can close the slides of chapter 4 and close the handout of chapter 4. Okay, please open the slides of chapter 5. Okay. Oh. Okay, so open. Okay, so let us see chapter 5. Okay, in chapter 5, we will introduce MIMO channel models. Okay, so this is the outline. First, we will give an introduction. Second, we will introduce MIMO channels in line of sight geometry. Third, we will introduce general channel model with correlation. Fourth, we will introduce Kronecker channel model. Fifth, we will introduce the impact of antenna correlation on MIMO capacity. And sixth, we will introduce the dependence of RT and RR on antenna spacing and scattering angle. Okay, we will give the definitions of RT and RR in this section. Okay, and seventh, we will introduce the pinhole scattering. And finally, we will introduce the line of sight channel model. Okay, due to the time limitation, we cannot finish teaching chapter 5. Okay, first let us see the introduction. Okay, a common assumption in MIMO analysis is that the channel matrix consists of independent, identically distributed, that is IID, complex Gaussian gains. That is H is equal to HW. Okay, do you remember what is HW? Okay, let us review it. Please open the slides of chapter 3. Okay, so there are some problems of my computer. So open the file. And this is chapter 3. And let us go to section 3.9.1. Definition of HW. So let us see the definition of HW. Let the magnitude of the elements of H be rarely distributed with sigma H squared being equal to 1 over 2. What is sigma H squared? Please see the previous slide. The real part of Hij and imaginary part of Hij are normal distributed a random variable with zero mean and variance sigma H squared, where Hij is the ijth element of the channel matrix H. So which implies that the expectation of the square of the absolute value of Hij is equal to 1. Okay, why? Okay, because the real part and the imaginary part of Hij are independent. Okay, that is, okay, are independent. Okay, so the variance of Hij is equal to the variance of the real part of Hij plus the variance of the imaginary part of Hij, okay, which is equal to 2 sigma h squared, and is equal to 2 times 1 over 2 is equal to 1. Okay, and because Hij is zero mean, so the variance of Hij is equal to the second moment of Hij, okay, which is equal to 1. Okay, and remember that because Hij is a complex random variable, so we need to add the absolute value here. Okay, furthermore, assume that the channel is spatially white, which means that the expectation of Hij times HMN conjugate. Okay, the star means the complex conjugate, and is equal to delta Im times delta Jn. Okay, so what is delta Im? Okay, delta Im is equal to 1 if I is equal to m, and delta Im is equal to 0 if I is not equal to m. So this is the discrete delta function, or discrete time delta function, and delta Jn is defined similarly. When these conditions hold, the channel matrix is denoted by HW. Okay, let us go back to chapter 5. Okay. Okay, in the real world, however, this is not always the case. In particular, correlation between the received or emitted signals, okay, that is the transmitted signals, to or from antenna pairs, or the existence of a direct line of sight component in the signal at each received antenna causes H is not equal to HW. Okay, in this chapter we introduce several analytical models for H that incorporate. Okay, what is the meaning of this word? Okay, let us see the handout. Excuse me. Excuse me again. Okay. Okay, so let us see, okay, page 5. Problem 1. What is incorporate? Okay. Solution: to include something as part of something larger. Okay. So let us go back to the slides. Okay, that incorporate the effects of antenna correlation and the impact of line of sight propagation. These models often appear in the MIMO literature and provide a convenient means, okay, that is a convenient method to compute the impact of antenna correlation and Rayson fading. Okay, we just introduced what is Rayson fading at the end of the chapter 4, as opposed to purely fading on the capacity of a MIMO system. Okay, it is 25 minutes. Let us take a break.